Alright, so a car is traveling at a steady 77 kilometers per hour in a 50 kilometer per hour zone. A police motorcycle takes off at the instant the car passes it, accelerating at a steady 7.4 meter per second every second. Okay, so I'm going to let you guys do the motion maps. You got one car. The speeding car is moving at a constant velocity, so the dots are equally spaced. Whereas the police motorcycle, the dots get further and further apart because it's speeding up while moving in the positive direction. So I'm gonna sketch. Let's see. Well, first we have an issue with units, right? So the velocity of the car. The units are what, 77 kilometers per hour, right? The acceleration of the motorcycle, however, is the police motorcycle, is like meters per second. I think it's 7.4 meters per second squared, or meters per second per 1 second. Okay, so that's a problem. So this is kind of annoying. We have to fix the units first. I'll just draw a horizontal line. And in 1 hour, in 1 hour, 60 minutes. And then in 1 minute, 60 seconds. And then 1,000 meters are in 1 kilometer. And I think now the units will work out to be the same, because we need meters per second instead of kilometers per hour. So kilometers cancels here. I'm really just multiplying by 1 3 times. That's all I'm doing here, just converting units. Minutes. Oh yeah, seconds is what I want. That's good. Hours. So the units I'm left with are the units I wanted. So I've got now I've got equals about 21.4 meters per second. That's 77,000 divided by 3,600. Okay. So now I have consistent units. I'm going to let t be the time when police moto catches up to speeder. Okay, and I'll just sketch a stack of graphs for both. So for the speeding car, here's a velocity graph, meters per second, right? Seconds. And I just have a horizontal line. That's constant velocity. So this is the speeding car. And I won't bother with the acceleration graph because, you know what? There is no acceleration for the speeding car. Now I know that the speed of the car, the speeding car, is 21.4 meters per second. So that makes the displacement for the speeding car, the displacement, delta x, for I'll just say car, is going to be 21.4 times t, right? Now for the police moto, I'll do that over here, police motorcycle. So the police motorcycle is speeding up the whole time. Okay? And I'll let t still equal the same thing. Okay? So police moto, I'm going to draw it like that. And that's v in meters per second still. Time in seconds. Okay? And here's my acceleration graph. it's just going to be a positive acceleration. So it's going to be a line like that. And we'll again say that t is this moment in time called t when the moto catches up to bike. Call that t, just for convenience. And let's say here. So I'll make my t correspond on both graphs. That means this height of the triangle right there should correspond to the area of our acceleration graph, our change in velocity for the moto, right? Change in velocity for the moto, again, we know its acceleration is 7.4 meters per second squared, so the change in velocity for the moto is 7.4 times t, where t is the time to catch up to the speeding car. So that makes, since the motorcycle started with 0 velocity, the change in velocity and the velocity when the moto catches the car are the same value, are the same number. But change in velocity and final velocity don't mean the same thing necessarily all the time, because you don't always start with 0 velocity. Anyhow, for this problem it's a little bit simpler. So we have 7.4 t is our change in velocity, so that's the height of that triangle. So we got 7.4 t. The base of the triangle is t, right? That's the time to catch the speeder, and we have to divide by 2. And this will get us our displacement for the moto, right? So I'll go to a new page now, and my basic idea here is going to be the displacement for the moto has to equal the displacement of the car when the motorcycle catches up to the car. So I'm just going to set the displacements equal to each other. I should also kind of reflect on this number here. You always want to ask yourself if that's reasonable. Well, you're free to look it up, and this turns out to be almost 50 miles per hour. So I'm pretty confident that conversion is a good one. Okay, so now let's set the displacements equal to one another on another page. All right. So I have, let's see, this basic idea, car and moto, that's the police motorcycle, will have the same displacement when the moto catches up to car. Okay? So displacement car equals displacement moto. So that's the logic I'm using to solve the problem. So the car's displacement was 21.4 t. The motorcycle's displacement was 1/2 7.4 t times t, right? And I can make this a little simpler. Half of 7.4 is 3.7. 3.7 and then t squared, right? And then I'll just leave the other side alone, 21.4 times t. Now, you should notice that you can divide both sides by t here. And that will actually divide, t goes in itself and make 1. One of those t's that was squared divides into the t to make 1. Okay? So now I have 21.4 equals 3.7 t. Divide both sides by 3.7. So I get t equals, it's close to, it's about 5.8 seconds. Okay? And so that's how long it takes the Moto catches the speeder after 5.8 seconds passes. I'm going to make a new page now because that's not all we can find. Once we find the time for their displacements to be the same, we could find out their actual displacements. And if we have the motorcycle start at 0 position, motorcycle and car start at 0 position, their displacement will be the same number as their position, because initial position is 0, so you're just subtracting 0 to find the displacement and position. We can find their positions when the motorcycle catches the speeder pretty easily. Actually, why don't I do it on the other side, right here. So you might wonder, where is the car and motorcycle? Where is the car when the moto catches it? Maybe that's a nice way of saying it. Might wonder that, right? And I'm going to use the simpler of the two equations is the car's displacement. So I'm going to use that one. I could use either one, right? So displacement car is just 21.4 t, right? So I'll just, so that's 21.4. This was meters per second, right? 21.4 meters per second times t, which is 5.8 seconds. That's what we just found. The seconds are going to cancel, right? And when the dust settles, you're left with about 124 meters. Now that's the displacement of the car, but that's also the displacement for the moto when the motorcycle catches the car. And if they both start at 0 position, that's also their position when the moto catches the car. So maybe I'll write a final statement. Both vehicles are 124 meters from where they started. And I'll say if we make 0 position, if we put our origin there, the location where they started then we could say that both vehicles are at 124 meter position at 5.8 seconds. That would just be imagining a number line. Here's where they started. They'd both be right here, and this is where they started. And you'll notice that that displacement is the same number, but again, displacement doesn't mean the same thing as position. Displacement and position are the same number when you start at 0 position, typically. Anyway, I hope that helps. Pretty interesting problem. Have a good day. Thanks for watching.